Alright, let's look at some further examples of definite integration. Integral from 0 to 2 pi of cosine squared d theta. So we're going to put together some of the integration techniques we already know, use substitution basically, and integrals of trig functions. Integral from 0 to 2 pi. Alright, so this is 1/2 of what? 1 plus the cosine of 2 theta d theta, right? And let's see here. So this is going to be, I mean, I can write down the antiderivative from that. It's 1/2 theta plus 1/2 the sine of 2 theta, and then that evaluates from 0 to 2 pi, right? Something pretty cool happens here. When I plug in 0, I get sine of 0, or I get sine of 4 pi. So this term drops out. Now, as we go on, this kind of thing I won't even write this part for, because I could have just as well noticed that from back over here, because, you know, cosine 2 theta has period pi, right? I'm integrating cosine divided by 2 over 2 full cycles, right? So cosine is symmetrically negative and positive over a full cycle, so the area, sine area plus and minus cancels out, and so like just from basic geometric intuition, I already know that this integrates to 0. I didn't really need to write that down, but I wrote it down just to assure you that in fact this green arrow to 0 is valid. So really, once I get to this, I could just be like, aha, so that's theta, you know, that's 1/2 integrated over d theta. So, I mean, this is nothing more than 2 pi over 2, right? Also known as pi. Okay, so anyway. Now, let's see here. If you, well, I guess one other kind of side comment here. If I was going to say integrate, think about this. If you think about the shape of cosine theta, right, and the shape of cosine squared theta over a full 2 pi cycle, you notice that those are the same, it's the same shape, right? So geometrically, this graph and that graph, it's the same graph, it's just been sort of moved around, part of the cosine squared. I mean, the same y values are attained, granted at different theta values, for y equals cosine squared versus y equals sine squared theta, right? So it stands to reason that these two integrals are equal. So this is also equal to pi by geometry. Another way you could see that, right? Another way to come at that would be that the integral from 0 to 2 pi, right, of 1 is 2 pi, right? But that's also the integral of cosine squared theta plus sine squared theta, d theta, right? So that's another way we could see, aha, well the integral of sine squared has to be equal to 2 pi minus the integral of cosine squared, right? 2 pi minus pi, pi. Anyway, so all of these things, pi, 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 pi. All right, so there's some tricks in my my arsenal. This one is not as pleasant. So anytime you have absolute value function, that's a piecewise defined thing, right? The absolute value of x minus 1 is equal to, what is it equal to? Well, it's equal to 1 minus x for x less than or equal to 1, right? And it's equal to x minus 1 for x greater than or equal to 1, right? Because that's what's needed to give a positive formula, right? If, for example, if x is like a half, 1 minus a half is 1/2, but if x is 1.5, 1.5 minus 1 is a half. So, I mean, this is what you need to keep positive. So this is actually, you have to break it up into two pieces. You have the integral from minus 1 to 1, right, of 1 minus x dx plus the integral, what, from, what do we got here, 1 to 3 of x minus 1 dx. Now, in this particular case, there might be a, let's see, that's length 2, that's also length 2. These might even be the same shape, just kind of shifted about. But anyway, I'll just do the calculation and not try to be clever here. But you've got to be aware of that if it's piecewise defined, you might have to break it up into pieces, short of some other insight. Okay, so that is x minus 1/2 x squared, evaluated from minus 1 to 1, right? And then plus 1/2 x squared minus x, evaluated from 1 to 3. All right. Notice, not surprisingly, that x cancels out. Excuse me, the 1/2 x squared term cancels out because you get minus 1/2 and then plus 1/2, minus 1/2, plus 1/2. This term evaluates to 0 because the top and the bottom terms cancel out. That's not surprising because it's coming from the integral of x, which is an odd function, about the symmetric interval of the origin, 1 minus 1 to 1, so that piece integrates to 0. Whereas this 1, the integral of dx from minus 1 to 1 is just going to give me 2. Right? Of course, that's what I get from 1 minus minus 1, which is 1 plus 1, which is 2. The other term, I will not try to be clever with. This is 1/2 3 squared, which is 9, minus 3. Parentheses are your friends. Minus, and then 1/2 of 1 squared minus 1. All right. And so what is that? We have 2 plus 9/2 minus 3 minus 1/2 plus 1. Let's see here, that's 8/2. Let's see here, so that's 2 plus 4 minus 3 plus 1. 6 minus 3 is 3 plus 1 is 4, I think. But someone is wrinkling a bag in the background, which is possibly corrupting my calculation. So if there's an error, I'm sure you guys will tell me about it. Thanks. All right, next example. Integral from minus 3 to minus 2 of dx over x. So the antiderivative of the natural log function is, natural log function. The integral of 1 over x is the natural log of the absolute value of x, evaluated from minus 3 to minus 2. If you hadn't put absolute value there, and you don't know what you're doing, you'd have soon found yourself doing natural log of minus 2 minus the natural log of minus 3, and then your calculator would go, what? Which is just the calculator's way of telling you you need to learn your calculus. Absolute values go there. Otherwise, it's not right. Because you can't take the natural log of minus 3 in this course. I guess you can take the principal logarithm of minus 3 or something if you're in complex analysis, though. So we have natural log of 2 minus the natural log of 3. The natural log is an increasing function. Its derivative is 1 over x, which means it's strictly increasing. So this is larger than that, and this is negative, and that makes good sense. I mean, I can simplify this. This is the natural log of 2/3. If you think about this geometrically, it's ever so very natural because the 1 over x function is a hyperbola rotated 45 degrees as it happens, and so we just calculated the area between y equals f of x, y equals 1 over x rather, and minus 3 and minus 2, which is something like this area right here. Of course, that's below the x-axis, so it's negative. By the way, the natural log of any number less than 1 is negative. All right, these things I tell to you without picking up a calculator. Okay, so there's three examples. Let's look at another example or two. Let's see here. Matthew's excited about something. Let's see here. Example 4. How about we look at the integral from 2 to 5 of x minus 2 over the square root of x minus 1. dx, of course. All right, so what we're going to do is we're going to let u equal to x minus 1. In so doing, we get ourselves du is equal to dx, right? And we also need to change the bounds. So like u of 2 is 2 minus 1, which is 1. And u of 5 is 5 minus 1, which is 4. And, okay, so that gives me the integral, right, from, well, the 2 changes to 1, the 5 changes to 4, And, uh-oh, x minus 2, huh? So what is x minus 2? Subtract 1 from this equation, we get u minus 1 equals to x minus 2. So that tells me how to get rid of the x minus 2. So what do I got? I got integral of u minus 1 divided by the square root of u du. So my u substitution was successful in the sense that after we make the u substitution, we have things that can be integrated with, you know, basic power law stuff. Let's see here. So that's see here, u to the 1/2 minus u to the minus 1/2 du. All right, so 1/2 plus 1 is 3/2, so it's 2/3 u to the 3/2 minus 1/2 minus 1/2 plus 1 is 1/2, which is 2. 2u to the 1/2. And all of that has to be evaluated from 1 to 4. So very convenient that in the u variable, these are perfect squares. It's almost like this is a book problem, which I just copied out of a book, and it has nice arithmetic. Oh, wait a minute, it's exactly like that, actually. Let's see here. So we got 2/3. 4 to the 3/2 minus 2, 4 to the 1/2, 4, minus 2/3. Oh, I'm stupid. I can't factor. 2/3 doesn't go out there. It's 2/3 like that, and minus 2 times that. All right. Yeah, I don't need this. Scratch that out. Okay. Minus 2/3, 1 to the 3/2. Let me put some big parentheses here. Minus 2. Hannah, could you please be less loud? Thank you. 2, 1 to the 1/2, like that. And let's see here. So 4 to the 3/2 is what? That's 4 to the 3/2 is really the square root of 4 cubed, otherwise known as 2 cubed, which is 8. So this is 2/3 of 8. Square root of 4 is 2. 2 times 2 is 4. So it's minus 4. Minus 2/3. Minus minus gives me plus. Plus 2. All right. So let's see here. That is 16. Oh, goodness gracious. 16 minus 2 over 3 minus 2, otherwise known as 14, minus 6 over 3, aka 8/3. Now, I sure hope the example I just worked is an odd problem in the book. That would be ever so lovely. Oh, yay, number 15. This is, okay, shout out. This is, what book am I looking at here? This is actually Howard Anton's Calculus, the 4th edition. It really matters not which book you look at, although Anton does a very good, very nice calculus book. This is exercise number 15, in the supplementary exercises in his section 5.9. I'm saying that out loud so I remember it. So here we are. Section, what did I say? Supplementary exercise number, I've already forgot it, 15. Woohoo, 8/3. All right, we have a winner. So there you have it. There's a slightly non-trivial U substitution. Sorry for the noise in the background. Let's see here. Another example we can look at here. Example 5. Suppose we're looking at the integral from 0 to pi over 2 of the 4th power of sine, and then we've got ourselves cosine x dx. So this time we're going to u equal to sine x. That makes du cosine x dx. Change our bounds. U of 0, sine of 0. U of pi over 2, sine pi over 2, right? Sine of 0 is 0, sine of pi over 2 is 1. So this one's really quite nice. After making the u substitution here, we're just left with the integral from 0 to 1, right? Integral from 0 to 1 of u to the 4th du. Oh, that's my favorite kind of integral. The answer is 1/5. Okay. Let's see here. Well, here's a nice one. Example 6. We have the integral from 1 to 0, awkward, square root of 1 minus 2x dx. Alright, so how do you do this? Well, u substitution again. I'm going to let u equal to 1 minus 2x. In so doing, I get du is minus 2 dx, right? So this is going to be the integral of the square root of u, right? And let's see, you're solving for dx. I get dx is equal to what? Du over minus 2, right? So du over minus 2, fine. But I got to change the bounds too, right? So u of 0 is equal to, plug in 0, so that's 1 minus 2 times 0, 1 minus 0. So u of 0 is 1. U of 1 is what? It's 1 minus 2 times 1, which is 2, which is minus 1. So the 1 bound changes to minus 1, and the 0 bound changes to 1. Look at that. After the u substitution, everything's right in the world again. Woohoo! All right, so integral, I mean, it's not one of these awkward integrals with the lower bound after the upper bound. Anyway, integral minus 1/2, the integral from minus 1 to 1 of, ooh, what? Sorry, something feels very wrong about this. U to the 1/2 du. Uh-oh. Oh. Yeah, okay, so now that I should put my glasses on. I'm looking back at the problem again. This is number 12 from the supplemental sections. I have missed a very important detail. See, this doesn't make sense because, I mean, the square root is not defined for non-negative things. So what I have failed to jot down, there's a little 5 in the right here. Now that makes all the difference because you can take the 5th root of a negative number. All right, so that there's a 5 here. Otherwise this wouldn't change, right? So it's just that's a 5th. So this is not 1/2, this is 1/5, and now that makes sense. Yay! All right, so this is okay. So 1/5 plus 1 is 6/5. 6/5, 1 over 6/5 is what? 5/6, right? So I do 5/6 times minus 1/2, which gives me minus 5 over 12. And then I've got myself a u to the 6/5 evaluated from minus 1 to 1. Also known as what? Let's see here. Minus 5 over 12, that's 1. And what? Oh. Well. Did I actually copy that down, right? Looks like I'm getting 0. Yeah, it's 5th power. Okay, well. All right, well. minus 1 to the, minus 1 to the 6/5 power is what? You could, I mean, two different ways you could look at it. One is minus 1 to the 6th power to the 1/5 power, right? Which is 1 to the 1/5 power, which of course is 1. So as far as I can see, that's -1, and so the answer is 0. Which, I don't know, it doesn't seem right to me right offhand. But, that is what it is. I'll tell you what, I'm going to stop video here and check myself, and then I'll come back. Thanks, guys.